Bonding in Solids by Phil John and Daniel Gaitan Jenkins. Molecular solids consist of atoms or molecules held together by intermolecular forces. Usually, intermolecular forces are weak in molecular solids. Melting point relatively low. Examples of molecular solids are H2O and CO2. H2O molecular forces are vary depending on each state as shown in the particle level diagram below. As a solid, H2O molecular forces keep the particles essentially in fixed positions. Why did the carbon marry the hydrogen? Because they bonded so well. Atoms that are held together using covalent bonds are stronger than the intermolecular forces. They also have higher melting points. An example are diamonds and graphite. Covalent network solids like diamond and graphite physically are completely different. But if we look closer at the particle level, we find that both are held together by covalent bonds in continuous networks, forming macromolecules. Ionic solids. Ions held together using ionic bonds. These bonds' strength depend on the charges of the ions. An example, sodium chloride has a melting point of 801 degrees Celsius, but magnesium oxide has a melting point of 2,852 degrees Celsius. Ionic solids form a lattice structure with positively charged cations attracted to negatively charged anions. This results in high melting points and boiling points. Basic types of ionic structures. Structures depend largely on the charges of ions and the relative size of the ions. An example of the different ionic structures can be found when we compare the structures of cesium chloride and sodium chloride. When attractions are set up between oppositely charged ions, energy is released. The more energy that is released, the more stable the system becomes. Sodium ions, being smaller than cesium ions due to the fewer layers of electrons, shrink the arrangement, bringing the chloride ions closer together, leading to repulsion. Any gains in attraction are cancelled out by this repulsion of the chloride ions. Metallic solids, also known as metals, consist entirely of metal atoms. Structures include hexagonal close-packed, cubic close-packed, or body-centered cubic structures. Bonding in metals are too strong to be covalent bonds because London dispersion forces and not enough valence electrons. This is a diagram illustrating how electronegativity of compounds affects their bonding in solids. Now you know why professors love to start the course out teaching about ammonium? Because it's just basic material. Here is an example of an AP question. Use principles of atomic structure, bonding, and/or intermolecular forces to respond to each of the following questions. Part A. At a pressure of 1 atm, the boiling point of NH3 is 240 Kelvin, whereas the boiling point of NF3 is 144 Kelvin. Identify the intermolecular forces in each substance. NH3 has dispersion forces and hydrogen bonding forces. NF4 also has dispersion forces, but instead of hydrogen bonding forces, it has dipole-dipole forces. Part 2. Account for the difference in boiling points of the substance. The higher boiling point for NH3 is due to the greater strength of the hydrogen bonding intermolecular attractive forces among NH3 molecules compared to that of dipole-dipole attractive forces among NF3 molecules. Dispersion forces found in both cancel each other out, neither affecting the boiling point of each compound. The melting point of potassium chloride is 776 Celsius, whereas the melting point of sodium chloride is 101 degrees Celsius. Identify the type of bonding in each substance. Both potassium chloride and sodium chloride have ionic bonds. Part 2. Account for the difference in the melting points of the substances. The difference in the melting points is due to the different strengths of ionic bonding in the substance. The charges on the cations and anions are the same in both compounds. Therefore, the relative size of the ions is the determining factor. Since sodium has a smaller ionic radius than potassium, the lattice energy of sodium chloride is higher than that of potassium chloride. Thus, more energy is required to overcome the ionic forces in the solid sodium chloride than in the solid potassium chloride.